Good morning, everyone. Welcome to session 5. My name is David Edom. I'm from the National Nuclear Security Administration, and I'll be moderating today's session. So we'll have 4 fellows speaking with us this morning, and first we'll start with Grace Johnson. She has done her practicum at National Renewable Energy Laboratory. Her field is in chemical physics, and today she'll be discussing with us quantum chemistry at scale.
Thank you. Hi, everyone. I'm Grace Johnson, and today I'll be talking about work I've done with my advisor, Todd Martinez at Stanford, talking about quantum chemistry at scale, specifically a project to generate two-electron integral code for multiple nodes, multiple GPUs. Okay, so first I'd like to give a perspective on quantum chemistry. So we've had this concept of computer-aided design around for several decades now, and it's gotten so good that we're at the point where we can design things like car engines and airplanes entirely on a computer without really much testing in real life. The same cannot really be said for things like materials design or drug design. And the answer for why that's the case is really just a matter of length scale. So on the length scale of drugs and materials, we have the pesky problem of quantum mechanics coming into play. So I think an interesting perspective on quantum chemistry is a tool that will help us basically bring drug discovery and materials design into a new phase going forward, where just like we design a car engine, we can design a drug entirely on a computer. So to do that, there are some advances we need in the field of quantum chemistry. So the goal of quantum chemistry is to accurately describe the behaviors and properties of molecular systems. So to do that, we represent a molecule with a wave function, and we have our Schrödinger equation, and we try to make an approximate solution to that equation. And if we do that well enough, we can learn things of interest about the molecule, like its energy or partial charge, things like this. But as chemists, we're interested in how things change, right? So we want to know, how does the molecule move in time? How does it interact with other molecules? So to give an example of this, I'll show a system that I worked on early on in my PhD. This is called the light harvesting complex in plants. And basically, the function of this system is to basically act like an antenna, absorb light energy from the sun and funnel that to the reaction center. So here I'm showing a dynamic simulation of the system, and what we'd like to do is figure out how the movements of the atoms there contribute to the function of the system. But I'll note here that this is a molecular dynamics, or MD simulation, so this is a classical simulation. And as we know, atoms are actually wave functions, so in a lot of cases, we need to be able to describe the system with quantum mechanical accuracy. But because quantum mechanics is quite expensive, dynamics has really been kind of relegated to systems of the size of this small molecule. So how would we be able to run dynamics on a system this large? There are lots of clever things you could do. So like Caitlin's talk yesterday, she talked about machine learning for quantum chemistry, trying to bring quantum chemical accuracy cheaply. But another thing we could do is just, are there ways to accelerate quantum chemistry calculations? And that's really where my work is. So it turns out the electronic structure problem, as we call it, maps really, really well to GPUs. And that's because the amount of compute you have to do relative to the input-output data is really high. So this is something that my lab has been working on for over a decade now. And we found that we can get a crazy speed up on molecules of different sizes when you run on a GPU, up to like 500x over a CPU. And this enables really interesting chemistry because basically we're making quantum chemistry routine in a way that wasn't done before. So we can study quantum systems that are the size of entire proteins. We can do reaction discovery. We can study excited state photodynamics, a bunch of really interesting stuff. So what I was interested in looking at is, what are some of the core computations that we need to look at accelerating? And is there room for improvement so we can go to even larger scales? So the answer to what is slow is often what's called an electron repulsion integral, or an ERI. So let's bring back our friendly Schrodinger equation. We can write down the Hamiltonian. There are several terms, the kinetic energy, the potential energy. But what we care about for our purposes is this electron-electron repulsion term. And if we write down the equations for that, it's this electron repulsion integral. Let's see if I can use this pointer. Maybe not. That's okay. But basically, it's a four-dimensional tensor, and you have two indices for the bra, two indices for the ket, if you're familiar with quantum mechanics notation. And it's basically a multi-dimensional integral over Gaussians. So we represent our electrons in our system as Gaussians. But in many cases, we don't actually care about the four-dimensional tensor. What we care about is that thing contracted with the density matrix D, which is basically the orbital coefficients of your wave function. This comes in two flavors, the Coulomb and exchange matrix. And the important thing to remember here is that this J and K matrix, these are sort of the expensive building blocks for a lot of quantum chemistry methods. So you've heard a lot about DFT during this conference. If you run a DFT calculation on a molecule and it's taking a really long time, chances are it's building a Coulomb or maybe an exchange matrix. So a couple things we want to do. We want to be able to scale our J and K calculations to multiple nodes so we can move to even larger scale. And another thing is we want to generate GPU code for higher angular momentum integrals. Okay, so what do I mean by that? I'm going to bring back some demons from general chemistry, orbitals. So you remember we have s orbitals, p orbitals, and then we can go to higher angular momentum like d, f, and g, and so on. So the reason I'm saying this is because if we want to compute these integrals efficiently, we basically have to block based on the orbital angular momentum. So we have the indices in the bra and ket. Each of those have an associated angular momentum. So what I'm saying here is for depending on the angular momentum, you basically have to have separate handwritten CUDA kernels for each group. So this is what was done in our group. People wrote handwritten CUDA kernels up to d angular momentum. And this is how we were able to compute this efficiently. So if we want to sort of achieve these two goals, what can we do? So we started looking at Regent. So Regent is something that a few of you know about and was actually mentioned in a talk yesterday. This is a task-based parallel programming language for high-performance computing, and it's built on the Legion runtime system. So this is a project that's been worked on by many people over a number of years, but we've been working with Alex Aiken at Stanford. And sort of the idea of Regent from a programmer standpoint is that you're going to use, your data structures are going to be called regions, and you're going to operate on them with tasks. And then the system will determine the parallelization for you. So instead of basically having to say, okay, this data goes to this GPU, and here's an MPI send and receive, all of that is sort of done under the hood for you, which is really cool. And it does this using a dependency graph. So if I tell my system, okay, this task operates on this data, then under the hood, the system can figure out, for instance, okay, tasks 1, 3, and 4 operate on independent sets of data, so we can actually run them in parallel. So what this looks like for our integral calculation is we just represent our density matrix, our ket and our bra in regions. We can partition these regions, which means to chunk them up. So we're going to do some data parallelism. And then we can generate tasks. So here I'm showing 18 different tasks to compute these integrals that can be done actually in parallel. So the idea here is that we're replacing that handwritten CUDA code with Regent tasks. But Regent gets even cooler than that. A feature of Regent is that it's hardware agnostic. And what I mean by that is you can write one code in Regent, and it will actually run on a variety of architectures. So this is the thing that's going to be able to enable us to scale our calculations beyond one node. There are also metaprogramming features. So this is going to allow us to generate new GPU kernels beyond D. And I'll talk about that in a couple slides. So what is this hardware agnostic thing? So say I was a little bit crazy and I wanted to do an electronic structure calculation on the entire green fluorescent protein. So I know I have to compute my J and my K matrix. I would write my functions, which are the tasks in Regent, and I also have my logical regions down below. This is the region data structures. And what happens is at compile time, these tasks will get compiled down into x86 assembly for a CPU and PTX for a GPU. And then at runtime, the system will take the code and the data, send that to a mapper, and the mapper's job is to farm that out to whatever processors you as the user give it, right? So I could give it a CPU, I could give it a GPU, or I could even give it a supercomputer. So Regent has for a long time supported NVIDIA cards, and now they also support AMD cards, which is super cool because me as the lazy quantum chemist only has to write one code, and then the hardworking people on the Regent team have made it such that I can run that on different architectures. Another feature is metaprogramming. So the idea of metaprogramming is that you write code to generate other code. And the reason this is useful for us sort of is beyond the scope of this talk. It's how you compute the integrals. There's basically a recursion relation to go from one angular momentum to another. And so we can encode that recursion within metaprogramming. And the upshot of this is that we can turn what was 300,000 lines of handwritten, hand-optimized CUDA code into about 250 lines of Regent metaprogramming. So to give the idea here quickly, we don't need to worry about the details of this code, but this is the actual metaprogramming code in Regent. And then at compile time, we have this metaprogramming stage where we produce generated code, which is analogous to the handwritten CUDA code. And then that gets compiled to intermediate representation into binary, which we can then run at runtime. So you may say that's great, okay, 250 lines of metaprogramming, but does it actually work? Is it as fast? And the answer is yes. So what I'm showing here is time to build the J matrix against system size for increasing the number of base pairs in a DNA system. And what we see is the Regent GPU, which is in blue here, has the same performance as the reference calculation, which is that dark green line, which is the handwritten CUDA kernels. We can also generate CPU code, and remember, I didn't have to change anything about my code. The Regent system just made it. And we see that that's about 100 times slower than the GPU, which we sort of expect. We can also look at multi-node scaling. So here's an entire calculation on a GFP. And I'm looking here at time per SCF iteration, which is an iteration to basically minimize your wave function parameters against the number of GPUs. And what we see is we can do a J and a K calculation in about 300 seconds on this entire system, which for those out of the field is quite fast. And these are on sort of older cards. These are NVIDIA Tesla K80s. We can look at the parallel efficiency, which is, this is the strong scaling, and we have pretty good strong scaling out to 45 GPUs. I don't have time to talk about the results for the high angular momentum stuff, but I'll just sort of give you the upshot here, which is that with that 250 lines of metaprogramming, we can generate code for all the way up to G integrals, and we see a GPU speed up for all of that. Okay, so I'm sort of out of time here, so I'm going to skip this takeaways slide and leave it for the website, because I want to talk briefly about a couple other projects I've been working on throughout my PhD. So one of them is looking at a distributed ab initio exciton model. So this is another light harvesting complex, like I showed on one of the first slides. So what we'd like to be able to do is, again, model the dynamics. So we want to see how this thing moves in time. And for that, we need really fast electronic structure. So a way to do that is to sort of coarse grain the system where we have individual quantum chemistry calculations for each of the chromophores. And then we couple them together with a simple Hamiltonian. And this is really great because basically we can do the chromophore calculations independently. And so I've been working on implementing something that basically gives a single server to each of the chromophore calculations. So that's work I've done at Stanford, and then also I have some projects at Stanford, and also I did an internship at NVIDIA for a quarter, looking at quantum circuit simulations with tensor networks. So tensor networks have a long history in both quantum chemistry and quantum physics. The idea is that you have some factorized, compressed representation of your wave function. And it turns out that representing dynamics of quantum systems is actually quite similar to representing quantum circuits. So we've been looking at a number of things. One of them is doing approximate simulations of Shor's algorithm for integer factorization, which has absolutely nothing to do with quantum chemistry, other than the fact that we're using sort of a quantum chemistry method to do the simulation. So if anyone has any questions about exciton models or tensor networks, quantum circuit simulation, would love to talk. I just wanted to mention those projects as well. So with that, I would like to thank especially my advisor, Todd Martinez at Stanford, the entire Martinez group, the Regent team, especially Alex Aiken, the folks I worked with at NVIDIA, and then definitely the Krell staff. This has been, a super amazing fellowship to meet everybody and to come here. So thank you.